Let's start a new video. In this video, what I want to do is sketch out the cross-entropy method in code. Around 50 videos ago, I actually described it. So if you want to take a look at, you know, at the actual explanation of what the cross-entropy method is, then go watch that video. In this one, we are going to do it in code first. Right now I'm feeling really lethargic and I don't feel like programming. I'd rather do pretty much anything else than this, but I need to continue going forward. At the very least, we need to try testing out training a agent that's based we need to try training out a neural network based agent using evolutionary methods and seeing how well that works. If it does, I think that will give me my motivation back. So, let's see. Right now, I am kind of, feeling lost. So, much like in the sketching out the CPR video, we are going to be at first doing things in kind of a pseudo-code, and then we'll move on to the actual implementation after that. I don't think I'll be doing this for like 8 hours like in the previous video. What I'm just going to do is set up the high-level architecture and write out the types, and then we're going to go into a time lapse where I code it all up. So first of all, I want to make an ensemble ID. Ensemble ID. The CPR also has this for dimensions. Now, let's take a look at the CPR. Let's close the primitives and let's go into this CPR thing. We have a bunch of tensor dimensions. We have a bunch of the types that are placeholders for tensor dimensions. Okay, we have this to initialize the graph for the CPR table. We have a bunch of utilities to get the action probabilities. Ensemble ID, world ID, action ID. It gets the model. Okay. We don't need to think about that. But what we have are these push trace, update trace, state path probabilities. We have apply updates. This actually applies the updates that have been accumulated to the actual model. We have the calculate updates, which propagates the CPR values, counterfactual regrets, I mean. We have a function for resetting the trace. And we have a pretty simple test here. Like here we push the ensemble ID, the world ID, and the player ID. And this is supposed to be emulating something like passing through the game. Like, for example, imagine that at the first step of the game, we have the ensemble ID like 0, we have this world ID, we have the player ID, and we push that into the trace. And at the end of the game, what we do is propagate the arrays, propagate the rewards from the other end. And we need to do something similar for the evolutionary algorithm. Unlike before, unlike here in the CPR module, we don't need to accumulate the trace. That's one of the big advantages of evolutionary methods. One of the other big advantages is that they work well with importance sampling. Policy gradients and deep reinforcement learning methods like actor critic don't work well with those. So because they don't need the trace, we only really need this part really. What we're going to do, we're going to have a tensor of let's write it out. We're going to have something like okay, let's open the core base. Open tensor m. And in fact, I don't think yeah, we've moved the types from the TensorM module into the core base itself. So right now we no longer need to open the tensor module just to get the tensor. So yeah, we're going to, let's call this reward tensor, and it's going to be tensor. It's going to be ensemble ID, and it's going to be, let's say, float. And in fact, instead of this, what I think we in fact need is the a numerator and the denominator. So the actual reward is first what? I mean, first of this element. Okay, let's make this a record. What the hell? Oh, okay, let's make this ratio. Float. First ratio divided by second ratio. I need to. I'm just putting in this ratio so that the comment makes sense. Otherwise, I don't have anything to name the element. Yeah, first ratio divided by second ratio. And you'll remember that we were actually, if you look at the, for example, let's go into the full, and we have the event loop. Okay, let's go into train. And we're basically doing this thing here where we have the rewards. No, actually, no. I meant to say, yeah, we have the state rewards. We have the rewards for both the players. And we have the total path probabilities. And when we accumulate these trace rewards, we do this. We multiply the reward by the ensemble path probability, and also add the denominator to it. So basically, this is what this reward tensor is supposed to be capturing for every ensemble. And then it's important that we have something like an ensemble ID, because I think we're going to have to add the rewards for. Yeah, we're going to have to add the rewards for both of the players. And the reward for the first player is the opposite of the reward for the second player. Of course, maybe it won't be strictly like that, because in the future we'll be emulating the rake. So the reward will always be less than the loss. But let's assume that the reward is that this is a zero-sum game, and that the reward for player one is the loss for player for the other player. And of course, if we only had a single ensemble, then this reward answer would always be negative. I mean, would always be zero. Sorry about that. But if we have multiple ensembles, then thanks to important sampling, we can, for every hand, compare the outcome based on that. So all the ensembles will end up having the different probabilities of taking a particular action, and that will allow us to calculate the rewards and accumulate them as we go along. I mean, so okay, let's for example make a something like a test. We're going to make a main. Uh, okay, I keep forgetting where anything is. Okay, let's make this test one. Yeah, we don't need this. Forget all of this for now. Open core CUDA. I mean, we don't need this either. But we're going to assume this is ran on the GPU. And we're going to have this, let's say, this push function. And we're going to be passing the reward into it. Let's say ratio equals something like 13 times 0.5, 0.5. We don't have the push right now. In our push, let's make this x equals file width to do. Okay, I don't feel like fixing all of that. Let's just leave this as a type error. And we also need the ensemble ID. And let's make this 0 here. Let's imagine we have like 4 ensembles. And okay, I guess they'll all get the. Well, no, actually, they might not get the same reward. Oh no! Actually, in a poker game, they would get the same reward, but they'll have different probabilities. Like this could be 0.3, 0.2. Okay, let's make this 8. And then let's say we might have like multiple steps like these, where we're getting different rewards. Like, oops, I didn't mean to select that one, last one. Okay, let's make this like so. And let's make this like something like negative. Let's make this a negative reward. And we could have something different here. Like 5, 8. Whoops, this should be. Okay, basically you see, you get the sense how we're going to be adding things into the reward tensor. So we have to get the reward tensor from somewhere. A reward tensor. And in fact, let's leave it like this. We're going to assume for the time being that we're just capturing the reward tensor from lexical scope. I need to take a short break. I'll be right back. Okay, to make it easier to understand, let's get rid of some of these. We have too many of these push calls. Let's make it step 1, step 2, step 3. And instead of naming this push, as I said before, it's actually more analogous to calculate updates. So let's make this like that. Yeah, now it should be fairly easy to understand. And after we have added all the rewards, we need to actually apply these updates to the model itself. And since we are basically capturing everything from lexical scope here, that's the assumption we are going with right now. We don't need to pass any arguments here. And what this apply updates function will do is apply the cross-entropy method updates. This is where the actual cross-entropy method will be made. So now let's actually do some of these functions. And of course, now that it's a top-level function, we need to pass all the arguments in explicitly. This will be the ensemble ID. This will be what? Oh yeah, the ratio. Type ratio equals ratio float. Yeah, I should have just copy pasted it from here. In fact, we don't need the record. Now that we have it factored out into a type. Let's see. Ratio, and its type is ratio. Isn't this kind of naming wonderful? Because over here now we'll need to pass in the reward tensor. I don't know from where, but let's assume that we have it here. Not bad. And we don't even have to think about this too hard. We can just get the code from here. Like we have this tensor atomic add, and we have to put in the index and the target tensor. So let's just put this here. In fact, let's change this. Let's name this trace rewards. We have the reward tensor trace rewards. We've renamed everything. Here we just need the ensemble ID. And here we have the ratio. Yeah, it's fairly simple what we have to do in calculate updates. It's not complicated at all. Why was this indented? An extra level. Let me just check out the CPR test again. Like, did I mess up the Yeah, I did. Okay, let's just do this. Okay, this is just a little formatting issue. Now we have the calculate updates, and this is its actual implementation. Maybe later I'll just decide to put the trace rewards at the end, but never mind that for now. The next thing would be apply updates. Apply updates. So what this should be are the let's call it weights. Wait, weights. And what we'll do is transpose those weights. So we need yeah, actually let's copy this. Uh, do I need anything else? I mean, maybe we'll have to pass in the grid object, but never mind that for now. Now I had time to think about what this should be. Let's just assume that this is a list of tensors. List tensor dim. Let's make it float. In fact, we could just make it an existential. Exists dim float. And this first dimension should be the ensemble ID. Yeah, the existentials are already proving to be useful for this. Now that we have existentials, we can express very exactly what we want this to be. We're just going to get this list based on the graph somehow, but we won't have anything to do with the graph in this particular module. This is a pure implementation. So now we'll just do the type for the transposed weights. And the way this will go is very simple. With regular weights, we have the ensemble ID as the first dimension. Right now, when it's transposed, it's simply going to be the last one. And that's all we need to do. Oh yeah, I do like this. Oh yeah, the only thing that is really occurring to me. Suppose we have something like the ensemble ID of 4. Let's go into the primitives module. It should be at the top actually. We have this transpose second, and here is where we determine the initial dimension, and then of course we create this short tensor, but then we take the minimum of the intended dimension and the actual dimension. And okay, this could be a problem because like the ensemble ID will be something like 4, and the the inner dimension will be, I think, quite large. Like it could be something like, let's say, 512 times 512. So we don't want to just take the minimum of 128 and 4 and minimum of 128 and this large number. It would be better if we actually they somehow distributed this value. Oh yeah. Okay. I guess we're going to have to get back to the transpose kernel later. Never mind this for now. Use rigid split. I had to pause to think about this a bit, and no, using rigid split would not work here. The reason why it wouldn't work is because rigid split takes in a single integer argument and dimension, which could be a compound type containing integers. Then it will try to distribute that integer evenly across the dimension in order to split it into two halves. But or here we actually need to, for example, I assume the size of is 4. What we need to do here is split it into tiles of 32 by 32. We cannot use a single integer to split it. So yeah, that's a problem. I guess we're going to have to come back and work on the transpose primitive more. It actually didn't even occur to me at all that we had a problem with how we were defining the shared tensor dimensions. Damn. So okay, let me not think about that right now. Even though I did get a pretty good idea. Let's go back to this, and here we have the weights and the transposed weights. So yeah, what we first have to do is transpose. We're going to designate. Let's see what's. So this is from and to. So let's make it like, for example, grid transpose. And the from argument will be the weights, and the target will be the transpose weights. Oh, oops, I need to do the writing. Wait, where did I put? It needs to take in a grid. Yeah, we need to use the grid transpose. This is going to be a grid-wise operation. And this is the source and this is the target. And after we execute this kernel, this function, it's going to transpose the weights into this transposed weights array. What we have to do is now, as the middle step, is just apply the cross-entropy method on the transposed weights. We also need the trace rewards in order to actually know what the rewards for each element in the ensemble should be. So let's add this that as an argument. And yeah, we'll implement the cross-entropy method later. And what this cross-entropy method will do is, it's going to calculate the mean, then mask out those below the mean, and then calculate the variance of the elements that haven't been masked out, and then it's going to mutate those which have been masked out. And we're going to get the new weights based on that. And inside the cross-entropy method, we only need to use the row map operation, and we will be able to implement the entire algorithm in local memory. It's going to be very nice. So after that, we just need to do the opposite of what we did here, like grid transpose grid. Here we have the transpose ways as the output, and now this will be the input, and the original weight tensor will be the output. It's just going to give us the results back. And yeah, this is the apply updates. Transpose weights, trace rewards. We can just use these as, let's just pass these as arguments for now. Now we don't have any type errors here anymore. We can see the exact types. Okay, let's go a bit further and actually create that grid, since it's easy. No problem. Let's open the ML primitives module. Open ML primitives. Oh yeah, we are already in the ML module, so we don't need to open ML, just the primitives. Oh yeah. These weights are actually a list. They aren't. They aren't individual tensors. I neglected to think about that. So I guess we're just going to have to iterate over them. For example, list them. Okay, let's do like weights, transpose weights. And this is the double pipe operator. List m. Oh yeah, we're also going to have issues with the existentials for this and this being different. Maybe we should, maybe the weights and the transpose the weights should be passed inside the same type, like for example here. Does make this a lot easier to handle. And now we have to extract the existential, exists, dim, float, and the first one is the weights. The second argument is the transposed weights. Oh wait, I forgot to close this. Why is this a type? Oh, right. I need to put in a comma here. And this is just a regular iter now. So we can just pipe it in like this. And the reason why we're writing it like this instead of putting the weights at the end is so the type influencer can propagate the types directly. It will be a lot easier than this. Like this, I mean. I mean, this grid transpose, if you think about this, what's going on? Yeah, it will do a transpose and then a cooperative groups sync. And it will actually be better if it didn't do this and let me do it myself at the end. That way, what we could do is transpose all of these weights into transpose weights in parallel instead of having to do a grid synchronization for literally every single weight matrix, or I mean weight tensor. But as pseudocode, this is very nice. We can just do this again here, grid transpose, and just swap things around. And now for the cross-entropy method, we can just pass the weights into it. Or alternatively, we can also do this weights thing like this. Weights list iter grid sync. Let me just put in a to do here. Grid sync. Grid sync. Oh. And we can just do this. Perfect. And we have what we have to do now is implement the cross-entropy method, and that takes in a dim the integer in the outer segment. So I think because we are using um, the raw map of we'll be using the raw map operation primitive to implement it, and it will be factorizing things into four. So yeah, unless the number of samples is smaller than four, it will have to be a multiple of four. That's it. That is, it can be one, two, three, four, but it cannot be five, six, seven, or nine. It has to be 8 or 12 or 16 for values higher than four. So I mean, let's implement the cross entropy method while we are at it. Now, CAM. Let's do it. Let's do this like so. And this is for our dim. Oh yeah, we have to put in a float here, and this is going to be the ensemble ID. And I suppose we could also pass in the grid here. But we're going to have to change the primitives. So this is not taking the grid. Okay, well let's assume that this exists for now. We're going to do sync grid here, and yeah, I think this is in cooperative groups sync. We also have in the primitives a grid raw map, and this is what we need. Unfortunately, this function will yeah, it passes the grid into this loop grid, and this does a cooperative groups sync grid at the end. And unfortunately, I do wish that we instead could go through all of the weights in parallel and do the grid synchronization at the end. So we're going to have to make a new variant of this. In fact, let me show you how it could be done right now. Loop grid. It won't be taking a grid. And since it won't be doing that, we could just do row map. Oh wait, no, not this. I meant grid row map. It doesn't take in a grid. But the thing about this, I mean, this loop is at a very outer level. So I don't think we should have been doing the grid synchronization anyway. Like in here, we could have just done then, like in okay. Let me show you what I mean. Of what the hell is going on? We're just going to get rid of the grid from here completely. We're going to get rid of this. Now we have this little grid here. Grid f from 2. And we can pretty much factor it all out like this. Yes, like this, from 2. And I forgot to remove the grid from here. Grid row. So we also have the this fucking map reduce. This will have to go here. Grid row of map reduce f from to map to reduce. And only one more. Oh yeah, we also need to put a quote here. Quote here. Where was I? Grid row map reuse. Okay. Grid row void. Oh yeah. F from 2. And then we also just need this. We can get rid of the grid from here. Oh yeah, perfect. Yeah, I think I've been kind of wondering in the past, you know, in the previous video, whether I've been doing the right thing by doing a grid synchronization inside these kernels themselves. And yeah, based on how this works, it seems like when it comes to grid synchronization, it might be better that we do it all manually outside the kernels. It's just something to think about. But if we are passing a grid into it, then we should be able to assume that it's going to do it automatically itself. Green room map. Oh yeah. I guess we also need to change the transpose. We have the grid transpose second. Transpose second. Let me just move this below. Of grid transpose second, green transpose. And we can just yeah, let's just leave it out here. I don't want any more complications with this. And in the test, yeah, since this kernel is the only one that's being run in, I mean, since the transpose is the only function, gridwise function that's being run in this device kernel, we don't need to synchronize it using the grid object explicitly. When the kernel ends, that will synchronize the grid. Yeah, not bad. And in the transpose itself, I think yeah, we are doing block synchronization here. Of course, we are. We definitely should be doing that in order to. Otherwise, the way we are using share memory won't be correct. Oh yeah, but oh, this has a huge issue. I can't believe that I missed this. There should be a device synchronization in between these. Oh, how the hell did I miss this? It's amazing that we got correct results despite having sync threads in between the loads and the stores. Damn. Okay, let's move on. We're going to have to get back to calculating the shared dimension correctly later. Never mind that for now. What we have to do is now implement the cross-entropy method. So let's do it. For that, what we need is simply the grid row map, and then we'll pass this into it as both the input and the output. Uh, Maybe later I'll just remove all the uses of a grid row map that takes in a grid and replace them with the regular ones. The ones that don't do the synchronization. Just a second. So yeah, now we have this in this extensor we have all the outermost the elements of this innermost dimension loaded. So what we have to do first, we have to calculate the average in local average config x and I mean, how many arguments does this take? So it it only takes 2. Why is this a problem? So this needs to be a number. Okay. Number. I'm guessing this also needs to be a number. No problem. So now we have the average, which is of type float. Now we have to create a mask. Inner mask local map fun x. Let's see, what do we have to do? We have to pass in the x, of course, and if x greater or equal than the average. If this is true, then these are the winners. So we have this mask. This is a tensor of booleans. Now I need to take a look at how the discrete sampling kernel was made, because in that kernel we are using the various masking functions. Yeah, we have the masked reduce in it. And we're going to do a masked reduction to calculate the variance, or rather the standard deviation. Actually, yeah, we need to do the we need to do the okay. First, let's make this variance. And this is going to be, it needs to take in a config. It's summing things up. So we need to zip this too. We need to zip the X and the mask. Tensor M. And this won't calculate the variance. It will just sum up the values. But if we, for example, let's make it a square of X, like local map X times X. Yeah. And actually, for when calculating the average of the for the cross-entropy method, we should, in fact, maybe just ignore the uh, this particular average. We don't need the whole average, just the average of the winners, I think. At least that's how I think it works. Let's make this let's call this the winner variance. We're going to call this the winner average. And we can put the average, in fact, like here. So we don't access it by accident, even though there's no chance of doing that anymore. I mean, there's no chance of that happening anymore. And oh yeah. We have to, instead of just taking the square of x, in order to calculate the variance, we first have to actually subtract the winner average from x, right? Sorry, I'm getting confused. Let's see, we have the winner variance, and in order to actually calculate it, we need not the square of x, not of this, but we have to. Okay, let's make this x, and then x equals minus winner average. Then we take the square of that. Okay, so we can actually do it like this. In all r, x minus winner average in r. Could we even maybe do we even have the square function? No, we don't. We don't have it in the core library. And instead of the variance, what we need is the standard deviation, in fact. And we can calculate that but just by taking the square root of the variance, like this. Why is this giving us trouble? Float number. Okay, I guess let's do this. Float. Let me just make sure that. Oh yeah, this is this returns true. Yeah, the when the original is greater than 0, and it will then reduce those true values. So it's not like it's reducing the false values actually. That's just what I wanted to confirm. So we have the winner average. First it filters out the losers here, then it calculates the winner average, then it calculates the average of the winners and their standard deviation. And now that we have those two values, what we need to do is actually generate, is use this to, let's actually rename this to the mean. And now what we'll do is generate new weight parameters using those two values, using the normal distribution. So what we in fact need here is the random number generator, and we'll map over the x, and this is going to be the return value, local map. We have to what do you think? Yeah, we just need the mask, I think, and nothing else. If this is a loser, then mutate it. Otherwise, return the original. Oh yeah, so we do need the original. So let's see, like this. If B, then X. Else, RNG normal. Actually, random. Let's do it. Random normal mean equals winner mean. So let's see, let's go into the random module and see where this thing is supposed to be. Here you have the normal. Generates a uniform value in the 0 to 1 range. And it doesn't take a mean and a standard deviation. Instead, we are going to have to do that ourselves. Okay, so wait, is this really how it works? I guess it, I guess it is. I guess this will have a mean of 0 and a standard deviation of 1. So let's just use this. Let's just generate the value. fact, let's just do this. Plus a winner mean, and this is going to be times winner std. And if we were programming on the CPU, we definitely want to have this be in the else branch, so it does less computation. But since we are doing programming on the GPU, we'll just put it here so it so the warp threads don't diverge. I guess it will be better like this. And no, what's the problem? Yeah, now it's assuming that this is a float at 32. I guess suppose I did this. This is still a float. Oh yeah. This ensures it gets it word as a f32. Okay, so okay, let's do it like this. Convert. Yeah. And what this does is if it is a winner, then return the original. In other words, skip it. And if it's not, just return a new value. That way, it will mutate every value in the ensemble to something else. Okay, and let's put in some constants, for example, to enable better parameter to enable better exploration in the parameter space, like cross entropy noise. Let's make it 0.1, something like that. And what this will be doing is adding noise to the standard deviation. If we set it as, if we just add this value to the winner standard deviation, that means the standard deviation will never be below 0.1. And that will always ensure that the parameters are getting changed. If you look at the video, like 50 videos ago on the Spiral playlist, you'll see that in the paper that I've showcased, adding the noise to the cross-entropy method was responsible for a large improvement in performance. And I think that adding a constant amount of noise like this worked the best. Otherwise, otherwise the entropy of the distribution would go down too quickly, and the performance would end up converging too quickly, too fast, I mean. Oh, what do you do? Oops. Yeah, I I actually keep forgetting that I have an undo button on my mouse. Maybe I should be using it a bit more. So yeah, I think this is the cross entropy method implemented on the GPU. It's pretty nice, I think. The only thing that we're missing is the RNG. So we can just pass it into the apply updates. Let's see, RNG from the outside. And we are going to create it in here. Let's see. Let's do a search for enol RNG. And we're creating it in a bunch of places, like here, for example. Random init random. I can just put in a reference here right now. RNG. Oh, I can do range m threads in grid from, and this will then convert it to a unsigned 64-bit value. This convert. I think this is actually it. Okay, let me pause here, and maybe we'll go into a time lapse after this, so we can figure out the correct. I mean, not the correct, but better shared tensor sizes for smaller. I mean, for uneven tensors. See you soon.